All right, this video we are going to formally define a continuous function and kind of what we use as far as limits and like a formal definition here. So there are three different main types of discontinuity that we need to know. The first is a hole. So if you have a hole in your graph, maybe this is x squared minus 1 over x minus 1 as your function, let's just say, and you have x plus 1, x minus 1 in the top. You find these cancel, and so f of x behaves just like the line y equals x plus 1 with a hole at x equals 1. Okay, and this just has a. Well, if that's the case, and that's the function that we're looking at, then that function is not continuous at x equals 1. In this case, if you have a hole that is not covered up, then that function is not continuous at a. In order for f of x to be continuous at a point, you need to make sure the function is defined at that point. So I would say in this example here, like f of 1 does not exist, or f of 1 is not defined. Therefore, this function is not continuous. F of a must be defined if I need to have a continuous function at x equals a. Let's go ahead and look at another example. So here's a piecewise example. And this is a jump discontinuity. Now, in this case, f of a is defined right here. So f of a you could find on the graph. And so it checks the box, so to speak, of that first one. However, the limit does not exist. If we take the limit as x goes to a from the left of this function, we get f of a. But if we take the limit as x goes to a from the right of this function, we don't get f of a. We get whatever this number is right here. Well, therefore, the limit does not exist. This is a jump discontinuity. And so therefore, I can't find the limit. This function is not continuous. So let's say we know f of a is defined. The limit exists. Awesome. So step 1, check. Step 2, check. We now get into step 3. That limit from both sides must be equal to the function value. So if I go through this list, on this one, f of a is defined. It's right here. The limit as x goes to a of f of x does exist. Let's just call it L. And let's call this f of a. But notice in this graph, those aren't the same. Okay, so we still have a hole, but that hole doesn't get covered up by f of a, so I still have a discontinuity here. The other type of discontinuity that is not in these three examples for the formal definition of a limit is a vertical asymptote. So here again are the three different types of discontinuities: removable discontinuity, jump discontinuity, and then infinite discontinuity, or what we know as vertical asymptote. So in this last case, just to give you an example, if I try to find the limit as x goes to a, now this goes to different directions. So let's go from the left, and I get a positive or negative infinity. Then by definition, that is a vertical asymptote. All right, let's look at this example right here. Using the definition, determine whether the function is continuous at x equals 2. justify your conclusion. So remember, the first thing I need to find is f of 2, is it defined or not? Well, let's look at this function. If I plug in 2 in the bottom, I notice I have an issue, but I also notice the top factors. So let's go ahead and factor the top. I have a whole at x equals 2. Since this is not a piecewise function where I then say, oh, and at f equals 2, we have 4, yay, I don't have that here. So f of 2 is not defined. There's a hole there, so not continuous. Now let's look at a piecewise function and see if we can figure out if this piecewise function is continuous. So I have a limit from the left. Here's 3. I have some values that are to the left of 3. There we go. And some that are to the right of 3. So my function over here is negative x squared plus 4. My function over here is 4 minus x. Now remember, the limit needs to exist at x equals 3 in order for this function to be continuous. F of 3 does exist. We would plug into our top one here, because that's where it's defined. I get negative 9 plus 4, so I get negative 5. So step 1, done. The limit as x goes to 3 from the left of this function is also going to be negative 5, because that's the function I'm looking at. But let's look at the limit as x goes to 3 from the right. Okay, so that's going to be the other function. So I have 12 minus 8, I have 4. Well, those two numbers are not equal to each other. Therefore, at x equals 3, I must have a jump discontinuity, because as I approach 3 from the left, I'm down here at negative 5. We can close that in because of the domain. As I approach 3 from the right, I'm up here at 4. So those are not going to be the same number. Jump discontinuity.